Welcome to the deep dive, where we take the source material you've shared with us and extract the surprising, actionable knowledge you need. Today, we are traveling deep into the foundations of computing, specifically the invisible architecture behind our microchips. And we're going to explore a concept that seems almost, well, childishly simple: the right angle.
It sounds simple, but it's a concept that drives one of the most fundamental trade-offs in any computational system.
Yeah.
I mean, it's really the battle between performance and flexibility.
Right. When you look at, say, the beautiful freeform curves in 3D rendering or computer graphics, that's all flexibility.
Exactly. But then you look at the floor plan of a modern VLSI chip, very large-scale integration, and everything is just meticulous. It's squared off, just horizontal and vertical lines, nothing else.
And this deep dive is all about understanding why that seemingly simple constraint, the source is called the orthogonal constraint, unlocks such profound advantages. We're talking about memory, we're talking about speed.
And the sources gave us this fantastic framework for it, a tale of two polygons.
I loved that. So on one side, we have the generalist, the polygon class, and on the other, the specialized hero of our story, the R polygon.
The rectilinear polygon. Our mission here is to really dissect the architecture of these two classes, and we're going to prove, using hard data and performance metrics from the material, why that specialization is the absolute golden key to high-performance computational geometry, especially when you're building something as dense and, as complex as a modern CPU.
Okay, let's unpack this. Let's start with the generalist, the polygon class. This is our jack of all trades. It's defined by a sequence of vertices, and it can handle, well, anything.
Anything. A triangle, a star, an approximation of a circle, some completely arbitrary shape with edges that meet at any angle you can imagine.
So this is the geometry you'd need for, like, general applications, game worlds, CAD design, maybe simulating fluid dynamics.
That's right. And that necessity, that need for maximum flexibility, it comes with maximum overhead. A polygon has to store every single vertex, every XY coordinate pair, and it has to use algorithms that are built to handle the crazy complexity of arbitrary angles.
Okay, so now contrast that with the R polygon.
Specialist.
Right, built for what the sources call discrete grid domains.
Exactly. Its fundamental defining characteristic is the rectilinear constraint. Every single edge must be strictly horizontal or vertical, period.
And that immediately ties it to these discrete grids. So the underlying manufacturing grid of a microchip, for example.
Or even something like the cadastral system that's used to map property lines in a city. It's all grids.
We saw in the sources this interesting architectural divergence. Wasn't just about the angles. The general polygon handles generic data types, right? Often floating point coordinates, decimals. But the specialized R polygon almost exclusively uses constrained integer coordinates. Why does that specific detail matter so much?
Oh, it's a massive performance and reliability advantage. For a chip manufacturer or a city planner, floating point numbers, decimals, they introduce precision problems. You don't want your circuit block to be at x equals 100.000000001 because the manufacturing tool, it operates on a discrete measurable grid. By constraining to integers, the polygon guarantees that coordinates snap perfectly to that grid.
So it's not just cleaner, it's actually faster. The computer doesn't have to wrestle with potential rounding errors or the complexity of floating point math.
You gain precision and speed at the same time just by accepting that grid limitation.
The design intent dictates the data type and the data type. It dictates the performance profile right from the start.
The moment you agree your world is only made of right angles and fixed grid units, you've set the stage for some really profound optimization.
And that structural choice right angles only, that leads us directly to what I think is the most remarkable insight from the sources, the core memory optimization. Here's where it gets really interesting. How does simply requiring right angles let us store only half the data?
It's a technique called even index vertex storage. And it's so clever because it leverages the implicit knowledge that's hidden inside that constraint. Okay? Think about the sequence of edges. If one edge is horizontal, the next one must be vertical. If that one's vertical, the next must be horizontal. They just alternate perpetually.
Right, so horizontal then vertical, H, V, H, V.
Right. Now consider three sequential vertices, V0, V1, and V2. To define a general polygon, you need to store all three pairs, X0, Y0, X1, Y1, and X2, Y2. That's 6 numbers.
Okay, 6 numbers.
But in our polygon, if the edge from V0 to V1 is, say, horizontal, then Y0 must equal Y1. And if the next edge from V1 to V2 is vertical, then X1 must equal X2.
Wait a second. So if I know V0, which is X0, Y0, and I know V2, which is X2, Y2, then V1 is It's uniquely determined. Its x coordinate has to be the same as v2's x, and its y coordinate is the same as v0's y. I don't need to store v1 at all.
Precisely. You've got it. The coordinates of the odd indexed vortices v1, v3, v5, and so on, they're implicitly known. You don't store them. You just reconstruct them instantly when you need them.
That is genuinely brilliant. But okay, doesn't the time you spend reconstructing that coordinate pair for every operation, doesn't that negate the memory savings?
That's the critical engineering trade-off. But the time cost of reconstructing a simple coordinate pair is trivial. It's a single memory reference and an assignment. That's far, far cheaper than retrieving two full data objects from main memory. Or worse, from disk. The massive win here is in the memory footprint.
So let's put this 50% reduction into the context of chip design. This is where it gets real. Imagine a chip floor plan with, say, 1 million complex rectilinear polygons, each one averaging maybe 20 vertices.
Okay, so with a general polygon approach, you'd need to store 20 million vertex objects. That's our baseline.
But with the specialized R polygon, where we only store the even indices v0, v2, v4, and so on, we cut that total right in half. 10 million vertex objects.
And the source analysis calculated that saving. It's approximately 240 megabytes of memory, just saved on vertex storage for that one layer of the design.
Wow.
And that reduction isn't just a number. It fundamentally improves system performance by increasing what's called cache locality.
Meaning more of the data you need fits into the fast CPU cache.
Exactly, which reduces all those sluggish trips out to main memory.
So the constraint eliminates redundancy, which gives you faster data access, higher throughput, lower memory usage, all because you enforced a right angle. That one simple rule completely redesigns the entire data structure.
And that memory hack is just the beginning. Once you've constrained the geometry, you can fundamentally swap out the computationally heavy algorithms you need for general shapes.
Yeah.
With significantly lighter, specialized versions, you just eliminate expensive math.
Okay, let's look at the point and polygon test. If I'm a computer and I need to know if a coordinate is inside a shape, what's the difference?
Well, for a general polygon, you use something called ray casting. You shoot an imaginary ray out from your point, and you count how many times it crosses an edge.
Okay.
But checking for that intersection requires some sophisticated vector math, primarily what's called the cross product calculation. That calculation is relatively expensive because it involves multiplication and subtraction on coordinates that, well, they might be floating point numbers.
And for the R polygon, what happens?
It's eliminated entirely. Since all the edges are axis aligned, you don't need a cross product. You just need simple, lightning-fast coordinate comparisons.
So it's just, is the point's x value greater than this boundary and less than that boundary?
Exactly. It's reduced to a series of bounding box checks. The constant speed up here is just enormous.
That makes so much sense. The complexity of the operation scales directly with the complexity of the shape you allow.
Precisely. And you see it again with area calculation. The general polygon relies on the robust shoelace formula. It works by summing cross products across all n vertices. It's effective, but it means iterating over every single point and doing complex math for each pair.
I know that our polygon version is still technically ON, but the sources suggest it's way more efficient in practice. Why is that?
Because its specialized summation formula works directly on the compressed set of even index vertices. The vertical edges, the ones with constant x values, they basically contribute nothing to the cross product terms in the math. They cancel themselves out. So you're calculating the area using half the points and much simpler arithmetic. The constant factors are just vastly smaller.
Okay, let's move to one of the more abstract tests, convexity testing. For a general polygon, determining if it's convex means checking every single internal angle to make sure it's less than or equal to 180 degrees. That sounds like a heavy calculation.
It is. It's in vertices and in cross product checks. But the R polygon cheats the system. It uses a geometric property called monotonicity.
Monotonicity. Define that simply for us. What does it mean to be monotone?
Okay, think of it this way. Imagine running a vertical line across the shape from left to right. If that line ever enters, leaves, and then re-enters the shape, it's not x monotone.
Ah, so a simple rectangle is x monotone because the vertical line only slices through it once.
Right, but a U shape is not x monotone because that line would cut through 3 times. And our polygon is convex if and only if it's monotone in both the x and the y directions.
So you're replacing n angle calculations with 2 quick checks, one sweep horizontally, one vertically, to see if the shape is simple enough.
Precisely. If it passes both monotonicity checks, it must be convex. It's an elegant, quick substitution that completely bypasses any need for angle measurement. And this pattern just repeats For edge intersection, the orthogonal constraint is so powerful it drops the time complexity from a potential O2 down to a reliable ON. Again, by replacing complex geometry with simple coordinate filtering. Specialization is truly the foundation of speed here.
All of this optimization, it leads us to the biggest algorithmic hurdle in physical design. Dealing with objects that are not simple and convex. We are talking about concavity.
Concavity is the enemy of efficient geometric algorithms. When a polygon has an internal angle that's greater than 180 degrees, we call that a concave or a reflex vertex. And this happens constantly in microchip design, where complex circuit blocks create L-shaped or Z-shaped obstacles.
Yeah, I found the analogy in the sources really useful here. If you're planning the shortest path for, say, an automated factory forklift, riding is easy if the storage racks are just basic rectangular blocks.
Right.
But if the racks have U-shaped cutouts, the forklift can get trapped, or the pathfinding algorithm has to search a far more complex space.
That is the computational headache. Concave obstacles confuse and slow down routing and verification algorithms. The solution in VLSI is rigorous convex decomposition.
Meaning we break the ugly, complex, concave shape down into a collection of simpler, manageable, convex pieces, usually rectangles, right, since those are the simplest rectilinear components.
Correct. The goal is to transform one complex problem routing around one difficult obstacle into a much simpler problem of routing around many simple rectangles. And the specialized R polygon decomposition algorithm does this really efficiently, using a recursive partitioning strategy.
Okay, walk us through the steps of that recursive strategy. How does the algorithm decide where to cut?
First, it has to detect the concave vertex. That's the corner that's pointing inward, the reflex angle.
Okay.
Once it finds one, step 2 is to select an optimal cut. It essentially draws an imaginary line from that concave vertex to the nearest other vertex or edge, but in a way that doesn't intersect the polygon's own boundaries.
So it's looking for the shortest, cleanest line segment that turns that one big reflex angle back into two smaller angles, both less than 180 degrees.
Exactly. Distance minimization is often used to make sure the resulting pieces are as large and efficient as possible. Then step 3 is the action. Split the polygon along that new edge, creating two subpolygons. And, crucially, the algorithm then recurses. It repeats the whole process on the new subpolygons until every single resulting component is convex.
And this decomposition is absolutely essential for VLSI. It's really the mechanism that makes high-density chip design computationally feasible.
Absolutely. It's critical for routing optimization because wire planning algorithms can treat those convex components as predictable safe zones. It enables effective partitioning, which supports hierarchical design where you break the chip into manageable regions. And finally, it streamlines design rule checking. That's the critical validation process. And it's infinitely easier and faster to check manufacturing constraints against a set of predictable rectangles than against a single complex concave monster.
So when we look back at this whole tale of two polygons, the ultimate lesson isn't just about efficiency.
No, it's about the philosophy of engineering. The generalist polygon is this massive container of possibilities, but it's burdened by the need to handle the absolute worst-case scenario. The R polygon trades away that potential flexibility for huge, huge gains.
It's the perfect illustration of application-driven design. Because chip layout lives on a rigid grid and only uses right angles, the engineer can replace computationally heavy general-purpose math, like calculating cross products across floating point coordinates.
With simple integer-based coordinate comparisons and highly optimized specialized formulas, the constraint isn't a limitation, it's a design feature. A feature that leads directly to a 50% memory saving and vast algorithmic acceleration.
So the choice between the generalist and the specialist class has to be dictated entirely by the requirements of the job.
Absolutely. For complex organic modeling, you need the flexible polygon, no question. But for building robust, high-performance infrastructure, whether that's a chip or a city map, the constraint or polygon is basically non-negotiable.
And this shift in perspective, viewing constraints not as barriers, but as tools for optimization, that's powerful far beyond just computational geometry.
And that raises an important final question for you, the listener. We've demonstrated monumental memory and performance gains just by imposing a strict rectilinear constraint in VLSI and urban mapping. So if eliminating those arbitrary angles can unlock such profound untapped efficiencies, where else in modern digital infrastructure, in logistics planning perhaps, or in complex database indexing, or in modeling any massive non-organic system, where else might we find huge untapped efficiencies simply by designing our models around a mandatory grid-based right-angle simplicity? Something to explore the next time you look at the map of a city street or the tiny architecture of a silicon chip.